Today we're going to talk about some techniques and some systems in Python for doing what we'll call metaprogramming, writing code that manipulates parts of our program, that manipulates other classes or functions or things like, or objects or things like that. Some of this will fit the familiar category of what we called reflection in Python or in Java, but some of the techniques that we'll look at are a bit broader than that. So we'll see here that we can call, add, or change things in classes or in functions or with object variables fairly easily without a lot of extra syntax, a lot of new classes that we have to refer to, like the class in Java, or field, functions that we have to get the fields from a thing, or a lot of things like that. In Python, we're going to be able to access and sort of tweak a lot of things pretty concisely, possibly in ways that could be dangerous to have such easy access to as well, but in short, sort of sometimes simple ways. So here, for instance, I've defined a very basic class called A. It has only a constructor that takes some value and saves it as an instance variable so that self.val is set to that val that was passed in as a parameter. That's all this class is able to do. So if I create an object of type A that has the string some value as its val, and another object of type A that also has some value as its val, initially, if I ask if A is equal to B, if those two different objects are equal to each other, I'll get back false, because equals by default, equal, does memory equality when the class doesn't have that underscore EQ function defined for it. But what I can do is I can write a standalone function. You see this one here that's called new EQ. It takes a self and an other, two arguments, pretty similar to an instance kind of function, a function that would take an instance of the class and do some stuff with it. It checks if the val variables of those two things are equal. Now, I don't have to call new EQ every time I want to compare two objects of type A, because I can actually modify the underscore EQ field of the capital A class and set it equal to that new EQ function there. And now, if I say A equal B, I will get back true, because the double equals will implicitly call to the equals operator here, that underscore EQ, and that is now set to be this function that checks val against val. So if the two objects have the same val, then they'll be reported as true. Yes, they are equal. So here we see not only would we have been able to access what the current EQ function is, like we might have done with reflection, we're even able to swap in a new EQ function there and make it the behavior for the class. We also can add static functions to the class. They need to take a CLS variable for the class itself. That's why they get called as a dot something, right? Is because they belong to the class. And so here I've defined one that I call new static, and it prints out the class's name as given to it. Now this is a little trickier because to attach it properly to the class, then I use this method type function from the types library, and that formats it into the right thing to be attached to the A class. So there's a little extra glue that needs to happen here, but once I've done that, if I call a.printName, it's going to print out A, the name of the class, and I could attach this print name to as many classes as I wanted to. so that I could print out the types of data that that my users are seeing in the program, or that kind of thing. So again, I'm able to access the static variables pretty easily because everything is looked up in some dictionary of what belongs to the class or what belongs to the object. And then I'm also able to modify those static or instance type functions for my class. Similarly, getting and setting instance variables, adding new instance variables, all of these are pretty straightforward as we've seen so far. If the class doesn't have a particular instance variable, I can just add one. I could say a dot something equals a new thing, and it would add it to it. If I create an instance, little a here, of the capital A class, I can see all of its instance variables simply by printing out the underscore dict dictionary for this class. That will print out the names and their current values. I can look up then within that dictionary. So I could have a user input the names of variables that they wanted to check the values of. And I could look them up using the square brackets as the key into the dictionary, and I would get out their values that way. I even can change the values of some or all of the instance variables by getting the keys list from that dictionary and then simply using those keys to change values or to access all of the values in that dictionary. So here what this code has done is it takes the name of each instance variable as the key, and it also sets that name to be its value. This is not a great thing to want to do in your code probably, but it changes every variable that belongs to that object A to have its own name as its value. And we could change these all to be whatever we wanted to, change them all to 0 or various things like that. Now, class variables, the class also has an underscore dict dictionary. This one is a little tricky because it also has all of the functions for the class in that dictionary as well. So this setting the values of things in that dictionary becomes an even worse idea in this setting because I would not just be setting all of the class variables like the test one that I named here to have themselves as their own value, have their names as their own value. I would also be taking all of the functions and replacing those functions with their names as the value as well. So this can be very bad, and in general, messing with the dictionary of the class. Oh, I'm sorry, this should be uppercase A here. Messing with the dictionary of the class can be very dangerous because you're replacing or you're messing with the functions as well as the variables. There we go. We fixed it so that they're all uppercase A there. So we even can add a new function only to a specific instance of a class. This is a little trickier because it's going to require a little extra glue to get things to attach properly. But I have that class A that only has the constructor and it sets the val for the object. So then I construct a little a instance of that. I write a function f that takes self and prints out the val from self. So it's just a print, sort of a print function for this class. But what I can do is I can attach that f function to only this specific instance of the class. This specific object gets a new function. So again, I do that types.method type. I give it the function and I give it who I want that attached to. And then it becomes attached only to that instance, so that if I created some new instance of the A class, it would not have f as a function. It would have only the things that are defined for the A class. So we can actually make variants of our types once they've been created. After they've been created, we can make a variant that has different behavior this way. And we saw this with the static variables, and that was a little, I imagine, surprising at that time that you could change the value of the static variables based on the instance. This similarly sort of, I don't know if shadows is the right word, but it gives a specific behavior to the instance little a that will not belong to any other capital A objects that I create down the line. So if I want one that's unique and has some new behavior attached to it, I could just attach that behavior to only that one or to only a certain set of them. So if I was writing a game and some player got a new ability or something, I could attach a new function to that player and enable that ability. And that wouldn't enable it for every other object of the player type. We can similarly get and call functions from a particular instance of a class. So this will look a little more like our Java reflection style here, but it's a pretty boiled down syntax for it. So we can do get attribute on an object, and we will get the particular thing that that object has if we know the name of it already. So we could do this with something like an instance variable like val, which we saw some things like that before for functions, where we were assigning instance variables to that function, sort of static variables for the function. But here, I'm able to get the functions that A is able to call, and then I call them. Or I could print out their names, or I could do whatever things I wanted to do, see how many parameters they have, different stuff like that. If I want to be a little more advanced, there are some good built-in libraries for this. The inspect library will let us check some different features and be able to get more about the specification of a particular function or a particular attribute from an object. So here, we're going for each name in the directory of A, meaning every name in the stuff that's accessible from A. This will include functions, whereas the underscore dict did not include functions. So this works a little differently than doing the underscore dict, which will only be the stuff that's specific to that instance. This will get the class stuff, like all of the functions that are defined there. So we get the attribute for each of those names from A, meaning that we'll get F1, F2, F3. We also would get variables if A had a val or stuff like that. We would get those here. So what we do next is we check and make sure that it's a method. Is it a method? Okay, so if it's a method, I'm going to try to call it. And here we're reporting that we're calling that particular name. We could have just said name here, but I wanted to show you that from the attribute, we can also get its name because everything has an underscore underscore name, or at least every function does, every class does, etc., like we saw for the class before. Here, then we use inspect to get the specification of what the arguments will be. So this gives us the names of the different arguments. I don't actually really care about the names here. What I care about is how many there are, because I'm going to give values for those different things. Now, the unfortunate thing versus Java here is that this tells us nothing necessarily about the types of those arguments. So we don't have a good way to inspect what the types of those arguments are supposed to be. Maybe the names would somehow indicate it, but we don't have a good way to say this one is supposed to be an integer or this one is supposed to be a string. And so for our purposes here, we're just going to give them all none. So I take none and I make however many nones are needed for this. And then I wanted to show you also, if I have a list of possible values that I want to feed in to a function, I can expand that list and make it the right number of arguments for the right set of arguments by putting a star there. That breaks the list up and passes each one as one of the arguments to my function. So ATT here is actually the function. It's a variable that holds that function, references that function. It also, again, could reference the variable that we're dealing with or whatever. And then down below, I can just call it like a function because it's a reference to that function. So again, we see some of this blend of functional style where functions are things we can pass around and we can do stuff with, but also this declarative style where we're going step by step and variables can change value and different things like that we can't do in a purely functional setting. So to do that sort of thing that we did in Java of looking at all of the pieces of a class or of an object is actually not too hard. The tricky part is getting the specifications right because nobody's going to tell us whether a particular thing was supposed to be an integer or a string or whatever because the types aren't declared for the parameters to those functions. So you may need to know something about your program in advance if you're going to do this sort of thing and inspect and get the arguments and use those functions in these sorts of ways. One other thing that can be done in Python that's a pretty neat set of features is decorators. Decorators are code that's written to wrap a particular function or class or object with some extra behavior or some extra guarantees to it. So I'll show you a few examples of this, but there are tons of great examples of how you can use decorators. They look sort of similar to the Java annotations that you might have seen at various times, like the @override annotation that you use in Java that says, I'm going to be overriding a method from a parent class, and if it turns out I didn't properly override the method from that parent class, then the compiler will throw an error. They look similar to those Java annotations, but they have their own sort of quirks and details about them. So here, for instance, I've written a function that we're going to use as a decorator to wrap any other function in the behavior of timing itself, telling how long it took. So the timed decorator is defined just like a normal function. The only trick is it takes a function as its input. And then when I'm wrapping a function, I use @timed before the function declaration, and it will just automatically feed this function in as the input to that, and it will give it the same name that it had originally. So it will make the foo reference point to a version of foo that is wrapped in this timed thing. So my wrapped function inside is what will sort of replace foo. We'll return this thing, which will inside call to foo or to whatever else we time here. And we'll see some other examples of writing timing because it can get tricky for different structures. So we start a timer, or rather we calculate or we record the current time. We call to our function and get its result. And then we record the end time. And then we're reporting this function took however many seconds because we're subtracting the end and the start and seeing how far apart they are. We still return the result of the original function so that if foo did have a result that it returned, that would still get returned at the end. And then the whole decorator returns wrapped because wrapped will just sort of be the replacement for foo. In my program, when I need to call something, I'll just call foo. And then it will do foo's job, and then it will tell me how long foo took to run and return the result that foo would have had originally. So this all just calls the original function, doing whatever other stuff needs done to it. You can see another example of this in my timeout code in the tests, I believe, for our assignments. I've used it in the past, and I think that's what I did for the timeouts for this one as well. So decorators can get tricky for recursive functions. Because factorial, if I replace factorial with a timed version of factorial, then when it calls to itself, that version will get timed. And any other recursive calls will get timed, and any other recursive calls will get timed, and so on and so on. I'm going to get, if I ask for a factorial of 100, I'm going to get 100 times reported to me from that call. That may not be what I want. I may not want it to actually time every single recursive call that happens for this. So when I want to use a decorator, and I know my function is going to be recursive, then what I do is I write a helper function so that the outer factorial gets replaced with the timed version of factorial. And the inner one is what's going to be used recursively. And so that way, the recursive calls don't get individually timed. I just time how long it took to do the whole factorial for whatever my parameter I was. Here's another neat application of decorators where we can do some storing or some caching with a decorator. So this takes an object as its parameter, and it is in fact a whole class. Decorators can be classes, they can be functions. It doesn't really matter because either of the two can take arguments and be able to be used in that decorator style of at something. So, this inherits from object, my apologies. So it has an initialization that takes itself and a method and possibly some name. What it's going to do is it's going to store the method and store the name, or just give itself the default of the method name. And then it has a get that lets you look up the value. You have to feed it an instance and the class that it's supposed to belong to. So it will call the method with that instance it will call the method with that instance to calculate the result if needed. It will then set an attribute on that instance with the proper name and the result stored, and then return that result. And this other part up here is for if it is return, or if it's called without any instance attached, then it will just return the self that was given there. So if the instance does not already have this if you're not provided an instance, then it will just give you back the self that was passed to it. But the main key thing of this is it says result is equal to calling my method with the instance that was fed to me. And then I'll set an attribute on that instance. So it creates an instance it creates a variable for that instance with the appropriate name and giving it the value of result that we just got from calling the method. So the method will only ever get called once. And from then on, the value is cached with the correct name on that instance. And this get will also return the result so that this call also gives us the correct value for it. So let's look at how that actually works. I have some class A that will take an X, some number, as its value to start off with. And what it's going to do is it's going to calculate factorial for that X. How it does that is it has a factorial function. But we sure wouldn't want to have to call that factorial function over and over again every time someone asked for the factorial of this. It would be nice to calculate it once and then save it forever. So essentially what it does is we attach cached attribute, and that makes it so that the first time factorial is asked for, it will call factorial with this instance of the object. And it will actually calculate the factorial. And then once that has been done at least once, it replaces itself. You remember that it sets an attribute with this same name, giving it just the value instead. So it essentially takes the function and replaces it, gives the same name to the value that was calculated from that function. So the first time it runs through, you say a dot factorial. That tells cached attribute, call factorial. And it calls factorial and it calculates the value and it would return it and print it out. Then the second time, it has already replaced factorial, the function, with the value of factorial 5 here, because this a was created with 5 as its x. So then, from then on, if I asked 100 times, whatever, it would never have to call the function again. I can say delete on it and force it to recalculate. That will uncache the stored value, and that will come back to where we now know that the instance, or that the instance does not already have that value, and we'll have to recalculate it again from then on. So this is a good thing we could do for something that's expensive to calculate, but we don't want to calculate it up front. We only want to calculate it if it's asked for. And then from then on, we hold on to the result for it. The other kind of use for this sort of decorator would be something like a network connection. That the first time someone asks for a network connection, we would want some function that establishes that network connection and then returns the established connection to them. But every subsequent time, we don't want to reopen a new network connection. We want to give them the cached version. So this is just an example of another type of decorator sort of thing that you can do in Python to take some existing behavior and wrap it in some other functionality. These can get quite complex, but can also do really neat and interesting things. So overall, the idea is that in Python, we're going to be able to do lots of metaprogramming that will range from the sort of stuff that we did with reflection in Java, like finding out what all of the methods are for a particular object, looking at all of its variable names, finding how many parameters a method has, though we can't see the parameter types because they aren't declared. But also metaprogramming in Python can extend into these interesting other categories where we can wrap up behavior in other behavior, mostly because of the fact that classes are objects and functions are objects. So when we create a decorator, that decorator can be fed a function and then add some new functionality onto that function, or do something before that function is called or after that function is called each time. And so because of this semi-functional, or this literally everything is an object sort of mentality, we're able to access a lot of things more easily than perhaps in some other languages, and we're able to build upon and wrap up more types of things than we might be able to in some other languages as we do this sort of metaprogramming stuff in Python.